Why doesn't a mosquito explode when it drinks blood several times its own weight? Think about it for a second. A balloon pops when you overfill it. A water bottle bulges if you pour too much liquid inside. Even our stomachs, as stretchy as they are, have limits that make us feel painfully full. Yet a mosquito, tiny and fragile, can pump itself full of blood until it looks like a flying droplet, and still, it doesn't burst. It's one of those little mysteries of everyday life that seems absurd at first glance. How can something so small handle so much without breaking apart? The answer, as we'll see, is a mix of clever engineering, hidden safety valves, and physics that would impress even the best human engineers. Let's start with the basic paradox. A mosquito can drink blood equal to 2 or even 3 times its own body weight. Imagine you doing the same. If a human weighed 70 kilograms, that would be like drinking over 200 kilograms of liquid in one sitting. Obviously impossible. Your organs, skin, and blood vessels would rupture, but the mosquito is built differently. Instead of soft, stretchy skin like ours, it has a hard outer shell made of chitin, the same material that makes up crab shells and beetle armor. You might think a hard shell would make things worse. A rigid container can't expand much, so shouldn't the mosquito burst even faster? This is where the hidden brilliance comes in. The exoskeleton is rigid, yes, but it's segmented like a suit of armor, and those plates can shift and stretch slightly at the seams. Think of it like the accordion folds of a camera lens or the joints of medieval armor. The body doesn't need to balloon out evenly like a balloon. Instead, it unfolds in tiny controlled increments, letting the abdomen swell in a surprisingly flexible way. Now add another piece of the puzzle: pressure. When you overfill a balloon, what kills it isn't just volume but internal pressure rising against weak, elastic walls. Mosquitoes avoid that fate with a combination of structure and active regulation. They're not passive bags filling with liquid. They are active pumps with feedback systems. Inside, their digestive tract isn't just a static tube. It's lined with tiny muscles that can contract and relax, redistributing blood and relieving pressure points. If one chamber starts to feel too tense, the insect can literally massage the contents along, spreading the load. It's like having an internal set of hydraulic valves constantly adjusting as blood flows in. But that's not all. Mosquitoes also have built-in pressure release systems. As they drink, they often excrete droplets of plasma, the clear, watery part of the blood, from their rear end. If you've ever seen a mosquito mid-feast, you may have noticed tiny droplets glistening behind it. That's not waste in the usual sense, it's a clever adaptation. By immediately ejecting excess fluid, the mosquito reduces the total volume it has to carry, keeping the concentration of nutrients it needs while dumping what would only add dangerous pressure. Imagine sipping a milkshake and spitting out water while keeping the sugar and proteins. That's essentially what the mosquito is doing, in real time, with its prey's blood. It turns the act of feeding into a live physics experiment, balancing intake and output to avoid overload. Let's use an analogy to make this even clearer. Picture a sponge versus a balloon. The balloon has a smooth surface that stretches evenly. Push it too far and pop, catastrophic failure. A sponge, on the other hand, is full of tiny cavities and pathways. Pour water into it, and the liquid distributes through many channels. It doesn't pop, it just gets heavier. A mosquito's body is more sponge-like than balloon-like. Its digestive system spreads the liquid, while its exoskeleton adjusts at multiple points. No single spot bears all the stress, so no single rupture point forms. That's why it can drink several times its weight without bursting. Still, this raises another question. Even if the mosquito can avoid bursting, how does it manage to suck up that much blood in the first place? After all, drinking is one thing, but moving that much liquid through such a tiny body seems impossible. Here, the mosquito's anatomy reveals another marvel. It has a proboscis, the long needle-like mouthpart, equipped with a sophisticated pump system. Inside are not one but 2 channels, one for injecting saliva that prevents clotting and numbs the bite, and one for drawing blood up. The pump itself works like a tiny piston engine. Muscles in the mosquito's head contract rhythmically, pulling blood upward against gravity and resistance. If you've ever tried to drink a thick milkshake through a straw, you know how hard it is. Now imagine doing it with muscles smaller than a grain of sand. That's the efficiency of mosquito biomechanics. Each pump cycle is tiny, but together they can move a massive amount of liquid relative to the insect's size. And let's not forget the physics of scaling. At human scale, moving liters of liquid quickly is tough. At mosquito scale, where forces like surface tension matter more than gravity, small pumps can achieve big results. The mosquito isn't fighting the same kinds of forces we would. Instead, It operates in a regime where its adaptations give it outsized power. Think of it like a flea jumping many times its body height. At our scale, that would be impossible. But physics plays differently for the small, and mosquitoes exploit those rules brilliantly. Now, you might wonder, why doesn't the mosquito's abdomen just split open from the sheer volume stretching it? Here's where microengineering comes in again. The abdominal plates are overlapped in a way that allows expansion but resists tearing. It's like expandable luggage with hidden zippers. At first, the case seems small, but then you unzip a hidden section, and suddenly it grows by half. Mosquito abdomens have similar tricks, with cuticle layers that can unfold and flatten to accommodate more blood. What looks like a hard, fixed shell is actually a modular system designed for expansion. The insect can go from slim and agile to bloated and heavy, yet still keep everything contained. Of course, this transformation comes with trade-offs. A blood-filled mosquito is sluggish, easier to catch, and more vulnerable. It's the price of success. But evolution has struck a balance. The insect only needs to feed until it has enough energy and proteins to reproduce. Once full, it doesn't need to fly far, just far enough to find a safe spot. And here's another clever twist. By excreting excess plasma as it feeds, the mosquito lightens its load even as it drinks. It's like fueling your car while simultaneously dumping ballast, so you never carry more than you need. Think about how elegant this is. A creature we swat at in annoyance is, in fact, a living demonstration of biomechanics, fluid dynamics, and evolutionary engineering. Its body is both armor and pump, both container and regulator. It's a system so refined that it can perform a feat we humans can only marvel at, safely carrying multiple times its own weight in liquid without bursting apart. The next time you see a mosquito hovering near your arm, you might feel irritation. But if you pause for a second, you might also feel awe. You're looking at a tiny natural machine that has solved problems of pressure, storage, and flow in ways we still study to this day. In fact, engineers designing micropumps and fluid handling devices often look to insects like mosquitoes for inspiration. Nature has been solving these problems for millions of years. And here's the kicker. This balance between intake, storage, and release isn't just clever, it's essential for survival. If mosquitoes didn't have these adaptations, they'd die every time they fed. Natural selection would have wiped them out long ago. Instead, their design is so effective that mosquitoes are one of the most successful species on Earth, thriving in nearly every climate and feeding on countless hosts. Their ability to gorge without exploding is a big part of that success. It's not luck, it's physics and biology working hand in hand. Here's another fascinating layer. The mosquito's survival isn't just about avoiding explosion in the moment, it's about long-term balance. A full mosquito is carrying a highly unstable cargo. Blood is thick, rich in proteins, and prone to clotting. If it sat too long in one place, the meal could harden and become unusable. To prevent this, the insect doesn't just expand, it processes. Enzymes in its gut break down proteins quickly, while other pathways help separate water from nutrients. It's like having a refinery built inside a soda can. As the abdomen swells, chemistry is already at work, ensuring the blood isn't just stored but transformed into usable energy and building blocks for eggs. This dual action, mechanical expansion plus chemical processing, means the mosquito doesn't just avoid bursting, it actively turns danger into advantage. Now let's zoom out and think about physics again. Imagine inflating a balloon until it's at its limit. One more breath and it bursts. That's because the stress is distributed evenly across a thin surface. A mosquito's body avoids this by distributing stress unevenly in a controlled way. Some areas take more load, others shift position, and excess liquid is pushed out. It's like comparing a fragile bubble to a reinforced submarine. Both are hollow, both are filled with fluid, but only one is designed with redundancies and escape valves. That's the mosquito. It's less a balloon and more a pressurized system, with safeguards at every step. There's also the matter of scale. At human size, forces like gravity and hydrostatic pressure dominate. At mosquito size, different physical laws take center stage. Surface tension, viscosity, and the strength of tiny structures relative to mass all play a much bigger role. A structure that would collapse at our scale is perfectly stable at theirs. This is the secret of small creatures everywhere. They can get away with feats that look absurd when imagined at human size. Ants lift many times their body weight. Fleas jump incredible distances. Mosquitoes drink multiple times their weight in blood. All of this is possible because at small scales, the physics of strength, pressure, and elasticity plays in their favor. But there's one more trick worth highlighting. The mosquito's cuticle is not just armor, it's alive. It can remodel itself slightly in response to stress. After a feeding, the insect doesn't just sit and risk rupture. Proteins in its exoskeleton adjust, helping it return to a slimmer profile as digestion progresses. That means the system isn't static. It's dynamic, changing shape and tension over time. Imagine if your suitcase could shrink again after you unpack it. That's what a mosquito's body does automatically with every meal. So what's the big eureka moment here? It's that the mosquito survives not by brute strength or infinite stretchiness, but by balance. Balance of intake and excretion, of rigid plates and flexible joints, of pumping action and chemical breakdown. It's a system designed by evolution to push the limits of physics without ever crossing them. And here's the poetic part. Every time we slap at a mosquito, we're trying to destroy one of nature's most elegant little machines. It may be annoying, even dangerous to our health, but scientifically it's breathtaking. This also shows us a broader truth. The world is full of hidden designs like this, where nature has solved problems that would puzzle human engineers. We look at a mosquito and see a pest, but inside that pest are solutions to pressure regulation, microfluidics, and material science that inspire modern technology. Engineers studying tiny pumps, flexible joints, and pressure release systems often turn to insects for clues. Mosquitoes, in all their irritating persistence, are also blueprints for future inventions. And that's the shift in perspective I want you to take away. The next time you hear the whine of a mosquito near your ear, don't just think about the itch to come. Think about the physics experiment hovering inches away. Think about the impossible feat of drinking 3 times your weight without bursting. Think about the little valves, the pumping muscles, the expandable armor, and the excretion system that make it possible. What looks like a nuisance is also a demonstration of resilience, adaptation, and balance at its finest. In the end, mosquitoes don't explode because they are not balloons. They are pumps, regulators, and processors all in one. Their bodies are not fragile accidents but carefully tuned systems. And when you understand that, you don't just learn something about insects. You learn something about the principles that govern all living systems. Adapt, balance, distribute stress, and survive. That's the hidden beauty of science. It turns irritation into admiration, annoyance into awe. So next time you swat at one, remember the secret it carries. A lesson in physics, biology, and engineering hidden in plain sight. If you found this surprising, imagine how many other everyday mysteries are waiting to be unlocked. That's what we do here at How It Actually Works. Take the ordinary and reveal the extraordinary inside it. If this sparked your curiosity, share this video with someone who's ever cursed a mosquito bite, and subscribe to join us on more journeys into the hidden mechanics of the world. Because every itch, every spark, every strange little detail is a key. And once you use it, you see reality in a whole new way.